This is a revision video for P6E, electric currents and magnetic fields and electric motors. When an electric current flows in a wire, it creates a magnetic field around the wire. The magnetic field is only there when there is a current. If the current stops, the magnetic field collapses. The shape of the magnetic field around a single wire is a series of concentric circles. If the wire is looped into a coil, then the shape resembles that of a bar magnet. When the wire is in loops like this, it creates something called a solenoid, and the magnetic field is the same as that of a bar magnet, with a north pole and a south pole, and the magnetic field lines run from north to south. If a current carrying wire is placed inside another magnetic field, for example in between the poles of two other magnets, the two magnetic fields interact. The magnetic field from the current and the magnetic field from the magnets push on each other, creating a force on the wire. This often makes the wire kick or move. This is called the motor effect. The force on the wire is always at right angles to the magnetic field. The direction of the force acting on the wire can be predicted using Fleming's left-hand rule. If the forefinger points in the direction of the field and the second finger points in the direction of the current, then your thumb will show you which way the wire will move due to the force. If the wire is parallel to the magnetic field, then there is no net force on the wire. You can change the direction of the force on the wire by reversing the direction of the magnetic field or by swapping the poles of the magnet around. You can also reverse the current in the wire. When we look at diagrams showing the motor effect, we often simplify them. And you can see that we use this notation for the direction in which the current is flowing. You can think about it like an arrow. If an arrow is being fired towards you, then all you would see is the tip of the arrow coming towards you. If the arrow is being fired away from you, then you will see the back end of the arrow moving away from you, and it will look a little bit like a cross. So when you've got current that's coming out of the page towards you, it looks like that. When you've got current going away from you or into the page, it looks like that. So in this diagram, we've got our current going into the page. So I want you to use left-hand rule now to work out which way that wire will move. Did you work it out? The field is going this way. The current is going down away from you into the page, so the force will push the wire downwards. Okay, so now it's time to see what you can do. I want you to stop the video and work through these 3 graded questions. Question 3 is a harder one, it's an A-star standard question. The motor effect that we just described is the basis behind every electric motor today. You can find electric motors in trains, hybrid cars, game controls, mobile phones, electric fans, disk drives, helicopters, food processors and thousands more other places. So the motor effect is very, very important to us. Electric motors transfer electrical energy to kinetic energy. No motor is 100% efficient. Whenever a motor spins, some energy is transferred to the surroundings and is usually in the form of wasted heat. This is a basic electric motor and it does make use of Fleming's left-hand rule, so you need to keep this in mind as we describe how it works. A simple electric motor has got a loop of wire inside a magnetic field. When there's a current in the wire, then a magnetic field is produced around that wire, and that field interacts with this magnetic field. One side of the loop is pushed down and the other one is pushed up. This is because the current in the loop is flowing in different directions. So this one is going that way and this one is coming down this way. So you can check the forces are right by using Fleming's left-hand rule. So because you've got a force acting downwards and a force acting up, this makes the motor spin. However, this just makes the motor spin backwards and forwards, and it's not always useful. For a motor to continue to spin in the same direction, the current needs to be reversed every half turn of the loop. Remember that this will change the direction of the force. So when you get to this situation, instead of the loop trying to be pushed up even more, it starts to be pushed down, and that makes the loop continue to spin. Now, this is only achieved by use of a split ring commutator, which is this bit here. Each time the loop is vertical, the current inside it reverses. The side of the loop that was pushed up is now pushed down, and it makes the motor spin round. Most motors can rotate at thousands of revolutions per minute. Have a think about how you can make a motor spin faster and how you can make a motor spin in the opposite direction. Okay, one thing you can do is increase the size of the current in the coil. You could also increase the number of turns on the coil, and you can also increase the strength of the magnetic field by using stronger magnets. These three things will make your motor turn faster. In practice, most electric motors use curved magnets. This produces a radial or a curved field. This means that current is at right angles to the magnetic field for a longer period of time. This means that there's a force acting on the wire for a longer period of time. So it makes the motor faster and more efficient. And that brings an end to this section on magnetic fields and electric motors. If you stop the video now, you can work through these exam questions.